Alright, so this is CSCI 305 Programming Languages lecture on program syntax and how we define it. So, syntax and semantics. The interesting thing is programming language syntax, or how it looks, and which also defines its form and structure, is defined by using a formal grammar. Programming language semantics is what they do. It's their behavior meaning. And unfortunately, this is extremely hard to define and is covered in Chapter 23 of the book, but we will probably not spend too much time on that in this class. We are more focused on the actual syntax and how it's going to work. So, well, in order to understand this topic, we're going to cover several things. Specifically, we're going to understand what a grammar and parse tree is. We're first going to look at examples, and then we're going to learn how to define a grammar using the Backus-Naur form, as well as what parse trees are. And then finally, we're going to start constructing grammars. Then we're going to look at the differences between phrase structure and lexical structure, and finally, different other forms for grammars. And so, if we think about a grammar, right, we all speak a language. Many of us speak more than one language. But when we look at English or just any other language, they all have a grammar, right? It's the way in which our language is constructed. And so, a grammar is the rules by which that construction can take place, and what it makes we'll say a syntactically or a properly structured sentence in our. So in this case, in a very simplified version of English, a sentence is simply a noun phrase, a verb phrase, and another noun phrase strung together. And so that's what this rule that you see is saying, where the S in angle brackets is the sentence rule, and it's composed of the NP, V, and MP rules, which are noun phrase, verb, and noun phrase. So noun phrase can then be further broken down into an article and a noun, and then a verb, in this case, in this really simplified version of English, can be one of the three possible words: loves, hates, eats. An article is a or the, and a noun can be limited down to dog, cat, or rat. And so what we can do is we can say that a grammar works by saying that it's really just a set of rules that define how we build a tree. And this type of tree is called a parse tree. At the root of this tree, at the very top of it, is the start rule. In this case, S in angle brackets. The grammar's rules then tell us how we build that tree, and what children can possibly be at the very leaves of this tree, right? So at any point, we can add in another child, which is one, which we fill in from one of these rules, and that eventually gets down to one of those words that we saw earlier, right? So, for instance, the rule S equals MPV MP says that we can add to the S node, we can add NPV and MP in that order as children. And so that kind of creates this type of parse tree, right? We start at the top, S being the root, then we have MPV and MP. And MP, the first MP breaks down into A and N, which then comes down to the and dog, and V goes to loves, and then NP, the second MP becomes A and N, which in this case was the and cat. So this produces this gives us the capability of producing a sentence: the dog loves the cat. A programming language grammar, on the other hand, is a little bit more restricted, right? We have certain issues with this. In a natural language grammar, the rules are a little more flexible, and they require extra information that we're not going to be dealing with when we come to programming languages, because we have no way to adding that extra information makes it intractable for doing what we're doing. But anyway, if we're looking at this programming language grammar, basically we're saying we have an expression here. And an expression can be defined as either two expressions, the sum of two expressions, the product of two expressions, or parenthesized sub-expression, or it can be the variables A, B, or C. And so, for example, if we have the statement in parentheses A plus B times C, we can break that down. We can create the parse tree for that, starting with the root rule exp, which breaks down into the first parenthesis exp, the second parenthesis, the middle exp breaks down into exp times exp, the first one breaking down to, in parentheses, exp, which breaks down to exp plus exp, which then breaks down to a. So that gives us the a plus b in parentheses, and then we have the times, and then exp, the last one breaks into c, comes down to c, giving us the entire sentence, right? So this is what the parse tree looks like. Now, for a little bit more definition of that, we'll work with BNF and the parse tree definition. So the Backus-Naur form, which was created by John Backus and Peter Naur when they were working on the Algol project, we have a significant number of different components. So on anything on the left side is what we'll call a non-terminal symbol, right? It's some symbol in angle brackets, and it's separated from the right side by a double colon and equals, right? That's the thing indicating that this is, we're saying that this rule is equal to, can be broken down into these specific sub-rules or tokens, right? So a production is simply how that actually works out. So the start symbol is also a production, but it's the special symbol that starts this whole thing. And then we have tokens, right? Tokens are just words that can appear, specific words or symbols that can appear as a part of the language, right? They're not a part of a production that can be further broken down. They're terminals of the terminal symbols or leaves of the tree. So when we want to define a grammar, right, we have four parts. We have the set of tokens, so these are the possible terminal parts of the tree. We have the set of non-terminal symbols, so the inner parts of this tree, and then we have the start symbol, which is the root of the tree. Now, and then we have the set of productions, and the productions are the description of how the tree is built. So tokens are the smallest units of syntax. They're strings of one or more characters of program text. They are atomic. They can't be composed of smaller parts, right? That's why they're leaves of the tree. The non-terminal symbols are larger parts of the syntax, right? These are things that they appear in angle brackets. They're not strings that occur literally in the program, but rather are expanded into strings of tokens. So that's the interesting part. That's why these are the internal parts of the tree, right? They are, and then possibly the root, right? That's what the start symbol is. It's the non-terminal symbol that forms the root of any parse tree for the grammar. The productions are the tree, like I said, are the tree building rules. So each one has left-hand side and then a separator in the right-hand side. In the case of standard BNF, the separator is a double colon equals. The left-hand side of any one of these is a single non-terminal. The right-hand side is a sequence of one or more things. Each can be a terminal or a token. A non-terminal or a token. A production gives one possible way of building a parse tree. It permits, essentially what it's going to do is it's going to permit the non-terminal symbol on the left-hand side to have things on the right-hand side in order as its children of the parse tree, right? Well, given that, there's possibilities that we can have more than one thing for any one non-terminal symbol. And so what you can either have the same non-terminal appear over and over and have multiple productions for it, or we can shorten that by having one instance of that non-terminal, and then for every possible alternative, we separate them using the pipe symbol or the vertical bar, if you want to call it that. So we can see an example of this when we're looking at the rule for, or the language for an expression that we saw earlier. So anytime that we saw we had a vertical bar, that's showing that we had multiple different alternatives, right? The first one was the sum of two expressions. The next one was the product of two expressions. The third one was a sub-expression in parentheses, and then the fourth, fifth, and sixth were the actual tokens A, B, and C, which are our variables. We could also write that, as I said, as individual lines, individual single productions. I always found that the alternatives was more readable and less confusing than having a bunch of the same one over and over. That being said, there's a special non-terminal symbol called empty, and what it's really standing for is just the empty string, or nothing. And it's really useful, for example, when we are doing, like, as we show here, an if statement, right? So if statement is, you have the token if, then you have an expression, then you have the token then a statement, and a possible else part. And then the else part can be either the token else in a statement or nothing. And so that's the interesting thing here, is we need to have, this often happens when we're defining a language, we often have to have the possibility for the empty symbol, right? Maybe there's a time when this is an optional rule. So, parse trees, right? So, when we're building those up, we always start with a start symbol at the root. And then we just work all the productions until we get down to what, based on, so when we have some line that we're trying to parse, we know what the bottom of the tree is. So we work the productions till we get to those token symbols. And so, and we do that by consistently adding children to every non-terminal, following any one of the productions that the non-terminal for the non-terminal grammar in the grammar, and we're done once we have reached all the leaves when all the leaves are tokens, right? So that's how we get there. That's how we build the parse tree. Our goal should be able to construct a parse tree for the given thing that we're parsing. So what I would like you all to do is take some time, pause this, and then try to build up a parse tree using the expression grammar for each one of these individual statements, right? So you have, first one is a plus b, the second one is a times b plus c, then in parentheses a plus b, then in parentheses a plus b in parentheses. So take a few minutes of your time, build up these the parse trees for these, and then we will continue. So now we are back from that little exercise. We need to understand what that whole concept was. We built these parse trees, and what this is really doing is, this is the first step in compiling, right? So normally we take a language, and even for, like, let's say Java or C, we have some piece of code, this program, and it's going to, we run it through the compiler, and the first step in compiling is called parsing. It's exactly what we did. We constructed a parse tree for a given program, right? And what it's going to, and so that's the first step in compiling, right? And unfortunately, for the context of this class, we're not going to actually talk about the algorithms necessary to do that, but we leave that to, I believe it's to the compiler's course, which is the 400 level, used to be the capstone. So moving along, right, understanding that that concept, we can define language. So now we have this concept, right? We can use a grammar, these types of grammars, to construct all the rules that we need to actually build up a language. And it gives us the capability of defining the syntax for the language. It doesn't tell us what the behavior of the language is, how that syntax is interpreted, but it does give us the capability to describe what the language is. So the language is defined by its grammar, and so anything that the grammar says is okay or is syntactically correct is in fact, any string that it can generate is in fact a string within the language, right? And thus can be derived as a parse tree for the grammar. The interesting thing is, almost always these languages are infinite, even though the grammar itself is finite. So that's almost a mathematically beautiful thing. But when we start understanding that constructing grammars is itself like programming, and the interesting thing is BNF is itself a language that can be defined using BNF. And for example, one of the most common language for at least for the to create parsers and compilers in Java, one of the major tools out there is called ANTLR. That's ANTLR, and it uses syntax very similar to BNF for describing the grammars that you use to then create parsers and compilers. But it is essentially, they wrote the most recent version of ANTLR in ANTLR in the previous version of ANTLR to build the tools necessary to create the new parsers for grammar for ANTLR. It's a little recursive in definition. Anyway, so this gets us into the next step, which is constructing these grammars, right? So now we understand what grammars and parse trees are. We understand how they're built up, and we understand BNF, so we can describe a grammar. So now let's look at how do we construct these things, right? So think about this. This applies the standard algorithmic design technique known as divide and conquer, right? We don't sit there and say, oh, well, I'm going to start here. I'm starting with the most basic thing, and I'm just going to build Java from scratch. You know, no big deal. No, that's insane. No one does that when they're making a language. We start out. We think about what are the things that we need to do, and we build those up piece by piece. Very small component, like for example, the language of Java declarations, right? Just the declaration of, for example, a variable. So it starts out, it has a type name and possibly a list of variables separated by commas, and it ends with a semicolon. And then we add in the concept that each variable can be followed by an initializer. In order to do that, right, we need to first start with just the basic concept, a type name and a declarator list, right? Okay, that's how we define a variable declaration. It's a type name and a declarator list. So then, what does a type name mean? Well, really, it's basically, it can be any one of the primitive types, which are listed here, and then it can also be any possible class or interface or array type. So we're not going to get into that part because the rule for variable declaration is actually quite large, and if you perhaps on in class I'll show that, but it's pretty nasty. But so we go back and we say, well, the next step is we have to describe what is a declarator list, right? And this becomes a little more tricky because it can possibly be either a declarator by itself, or a declarator, comma, a declarator list, right? So it becomes a recursive notion. So now we are now that we have that right, the leaves of the variables. So this leaves. So now we've gotten a declarator and a possible declarator list. So we still have to describe what a declarator is. And that leaves us with, and this can just be, a declarator becomes, really, it's a variable name, or possibly a variable name, the equal sign, and an expression telling us what the initialization is. If we were to really do this, we'd have to have the possibility to have square brackets in there, right, because of arrays. Then there's the special syntax for array initializers. This becomes, as you can see, it becomes very complex when we're trying to describe an actual real language that we're working with. So this gets us to the difference between phrase structure and lexical structure. So the question becomes, where do these tokens that we actually have come from, right? So tokens are just essentially pieces of program text we choose to think of as being built from smaller pieces, right? That don't come from built up of smaller pieces. So that includes identifiers, so like variable names, class names, all types of names, keywords, right? So the basic keywords of the programming language. For example, in Java, you have all the different modifiers. You have class, package. You also have void is in there. Then you have all the structural keywords like if and while and for. So all these things, and then the potential for constants, right? So you have integer constants, Boolean constants. You have string literals. All these things are potential tokens that can be in there. So the problem is that essentially programs stored in files are just sequences of characters. You can think of it as one really long string, and so we have to. The problem is, and this is so in parsing is really broken down into two steps, right? The first is scanning, and the second is lexing. And lexing is the part that breaks things up into tokens. Scanning breaks everything up into tokens after removing all the white space, which we'll talk about. So, lexical structure and phrase structure, right? So grammars so far, the grammars that we've been working with are all described as phrase structure, right? It's all the different tokens, and we just assume they're separated, right? By some sort of what we call white space. So any type of spacing, new lines, things like that. Well, the rest of that stuff is the lexical structure. Because we have to describe how do we divide this thing into tokens. And so essentially, there's two ways to do this. We can either describe a grammar that combines everything together, or two separate grammars, one for the lexer, one for the parser. And if you put it all together as one, you have to include all things like white space, and then which can include new lines and spacing and all these different things, as well as all of the tokens, keywords, things like that, and then all the rules that are define the syntax of the language. So it ends up becoming really cluttered with all this extra lexing business, and we just kind of need to get rid of that. Well, one of the things that a scanner does when you're in the parsing phase is it actually finds a lot of those new lines and comments and all that type of stuff, and gets rid of it. So before we or condenses it down before we ever actually see this. And so this is all this stuff put together is the reason why we want to separate these grammars out. The first grammar tells us how we construct a sequence of tokens, and in other words, it tells us the things that we don't need to consider. That gives us the potential for what are the tokens. The second one tells us how do we take those tokens and construct a parse tree so that we can actually turn that into a usable program, or we can actually interpret or compile that program. And so what this is showing us is we have program file, we have end of file or element, and then more program file. And then the elements are broken down into tokens, white space, or comment. And white space is broken up into spaces, tabs, and line. And tokens are either identifiers, operators, constants, and any other possible type of token. So this is how that works, like I was talking about. So the scanner reads, so the compiler is broken up into separate passes through a file. The first pass is the scanner. The scanner reads the input file, divides into tokens according to the first grammar. Then it discards all the white space and comments and keeps only the tokens, so it creates basically a token stream. Then the parser constructs a parse tree by using those tokens and then operating on the rules, using the rules of the grammar, the second grammar, to actually construct the parse tree. So the interesting thing about this is historically, this was not always the way it was done. And so you look at early Fortran, early Algol dialects, and you could have spaces in the middle of keywords. You could have spaces just kind of anywhere. And then same with and then other languages like PL1 allowed keywords to be used as identifiers. Essentially, this made this extremely difficult and made the algorithms really hard to write to be able to actually conduct this parsing and scanning in a we'll say a sane and efficient manner. Furthermore, when you look at these programs, it makes them very difficult to read. It's like looking at if you had a while keyword where it was WHI space LE, or you used the same, if you had a variable named while and then you had a while statement, that would not make much sense. That would actually make it really difficult to understand what's going on when you're trying to read this. Furthermore, there are some languages, right, which have specific white space restrictions. For example, COBOL had specific column positions that became significant. And a lot of that stuff actually, and what's referring to when it says card here on the slide, is that back in the old days when we were doing things on punch cards still, you had certain columns had specific information that was indicative of what was going on, and was more for the mechanical reading of the cards than it was for coding. Or furthermore, they might even, for example, a lot of times to try to save cards, they'd actually add extra columns on there that weren't technically okay. And that became a significant issue when converting from cards into actual files. But anyway, this was more of a problem for like old school Fortran, COBOL, and BASIC back in the days when cards were a thing. Most modern languages are free format, with the exception of, for example, Python. Right? Python has white space considerations where you have to ensure that blocks inside, for example, like an if or a function, are the statements inside there are on the same column. Otherwise, it gives you an indentation error and is very annoying. All right, so we've kind of gone through and looked at phrase structure, lexical structure. We know how to construct these grammars. We've seen what BNF parse trees look like. Well, there are other ways. So BNF was the initial way of describing these grammars, and but you know, when you try to write these grammars out, BNF is a very long-winded way of doing it, and so that we've over time have developed extensions to make it easier to write these grammars. And so there's different variations of BNF by itself that is just more to make it look pretty, but there's also extensions to BNF, which we call extended BNF, and then there's also another form called a syntax diagram. So BNF variations have used different ways of separating the non-terminal from its actual productions, as well as some things don't use the angled brackets. They just use distinct typefaces. For example, Antler it uses a form of BNF that does not use that uses the equal sign and does not use angled brackets. And then some even allow you to use single quotes around tokens, so you can distinguish the vertical bar in quotes from the vertical bar as a meta symbol. So just so we are all aware. On the other hand, eBNF has this. So if we recall from when we were looking at the variable declarator, right, we had to create the variable declarator list, and then from that. So that we could use and have the comma part in there, right? So we create that list in that recursive fashion. Well, eBNF allows us to get around that by not having to have maybe not having to have a separate rule for that, but instead we can use repetition bracketing and optional bracketing as well. So that's the interesting thing here, right? Is if we use curly braces around some portion of a rule, we can that portion can be repeated 0 more times. If we put square brackets around something, that means that it is essentially optional. In other words, it can occur 1 or 0 times. And then we can use parentheses for grouping things together, and within those parentheses we can also use the vertical bars. So whenever we hit that group, we have multiple alternatives in there, and it can be one of those alternatives for that section, and then it continues on, right? And then anytime we see quotes around tokens, or we use quotes around tokens in order to say that we want that specific string, not the meta symbol. So that helps us improve readability while reducing confusion for the actual parsing algorithm. So now if we were to look at this, right, we can ask ourselves, okay, what's going on here? Well, so if we're creating this if statement, right, we have if statement, and we say, well, if, and then an expression, then the keyword then, and then a statement, and then optional with the square brackets, else keyword, and a statement. And then we can have a statement list, and that can be one or zero or more statements followed by zero more statement with a following semicolon. So that's creating like a listing of statements. A thing list, which is essentially one or more of either a statement, zero or more of either a statement or a declaration followed by a semicolon. The mystery one is telling us now, what is this asking us? What is so I'm going to leave this to you to think about what mystery 1 and mystery 2 are. And we'll move to the question is, so what makes something an eBNF? Well, extended BNF is essentially anything that has some extension to BNF. So that can be all sorts of different possible extensions, and there's lots of different ones out there. But they all are pretty easy. Once you know these basic rules, it becomes pretty easy to understand. Some follow a little bit more, have gained a lot of, we'll say, insight from regular expressions, and can use some of the symbols from regular expressions to help us expand into and extend the BNF syntax. This brings us to a different way of thinking about a grammar, right? So instead of writing rules the way we have, we can actually visually depict them. And so we start out, and they're called syntax diagrams. So we start with an eBNF grammar, and then we can create this visualization of it. And so essentially, they're pretty easy to construct, right? If we look at this very simple one where we just have an if statement, and nothing really, no optional, none of that stuff going on. Essentially, the if statement, we have two things we can do. We can either have an oval for a terminal symbol, which is a token, or a square for a non-terminal. So something that refers to another rule. And so we can just build those up. And we can construct this for even things that have options, right? We just draw a line that goes up and around it, so it's bypassing that section. And so this becomes a very concise way of diagramming what's going on, until we get to things where there's lots of possible alternatives, which gives us branching, right? And so when we look at the nice, concise expression, it if we recall, looking at how this was, we go back to seeing a whole bunch of the same, like we had 6 possible alternatives when we have written it out as individual productions, and we see the same thing going on here in the diagram. But it's pretty simple as long as we understand what's really going on and how we can break this down. Once we have that, the diagramming technique is very easy. Everything always flows from the left to the right. We use arrows to go in between every single individual component, and that's how we build this diagram up. It's quite easy. The final one is loops. So this is where we have the curly brackets could be 0 more times, right? And so for this one, it's the addendum, where we have we know that we have to have at least one addended item, and then we can have plus, and then 0 more pluses followed by another addended production, right? So using that, so this is the interesting thing. As I was saying, it's pretty easy to read these, but the precision that we can gain from this actually becomes difficult because we have to follow and see all the different lines and what they actually can mean. And furthermore, and it's always the same with everything. It's very difficult for machines to process pictures easily. Really easy for machines to process text, very difficult for them to process information visually. And so that's sort of the downfall of the syntax diagram. It's easy for humans to read it, hard for machines. Finally, so this is the interesting thing. I know a significant number of you are taking theory right now, and hopefully, if I recall, the first section of theory gets into the study of automata and specifically languages and grammars. And so you'll get into the study of the formal languages, automata, and grammars, and how they're expressed. So they use a similar but quite different notation, where you have rule production that is described by some symbol that which falls with an arrow separating, and then you have the rest of the rule, right? And the epsilon symbol stands for replacement for the empty, or it's the empty string, which is the same as empty in angle brackets in BNF. But you can you essentially write a formal grammar in this. You can convert that to BNF quite easily if you know what you're doing. But here, small case letters tend to be terminal symbols, and uppercase letters tend to be productions. So anyway, there are also other types of grammars, right? Context-free grammars. Programming languages are almost always a context-free grammar. There sometimes is a little crossover with a context-sensitive grammar. And so there's a hierarchy of grammars, or a hierarchy of languages, where regular languages are the weakest of, or weaker at least, than context-free grammars. Context-free grammars are weaker and subsumed, actually, by context-sensitive grammars. So every regular grammar is a context-free grammar, but not all context-free grammars are regular grammars. And then all context-free grammars are context-sensitive grammars, but not all context-sensitive grammars are context-free. So, interestingly enough, a type of grammar that is context-sensitive would be like the grammar for natural language like English, Arabic, Chinese. Any of these things, they are context-sensitive grammars. They require information about what's going on in the sentence in order to understand, in order for the sentence to be actually processed correctly. Beyond all that, there are other variations beyond, but for the most part, the BNF and eBMF ideas are kind of flow through all of them. It's just the exact notation tends to differ. But as long as you understand the basic ideas that we've covered in this lecture, you should be able to easily pick up what's going on. As a part of this class, we're not going to be asking you to be able to process these other types. It's just you need to be aware of them. For example, if you're using tools such as Antler, if you take compilers, or any other parser generator, where you actually have to write a grammar, you need to understand and be able to use the techniques that you learn here and translate them to the way you write the grammar for the tool that you're going to use. An example of this would be from the Java language specification, which was written using a slightly modified version of basically BNF, where you use different typeface and without the angle brackets, and the separator is the colon. But everything is pretty much the same. They do have some subscripting to describe optional items. For example, if we look at the basic for statement, right? It starts with for, then a parenthesis, and then you have 3 productions, each separated by a semicolon. And they're all optional, right? You don't have to have that. But the semicolon itself is not optional. And then you have a statement after it. So thinking about what's going on there and what it means is it's not too hard to really figure out what's going on as long as you understand the basic concepts of BNF and eBNF. in conclusion, basically we use these types of grammars to describe any type of programming language syntax, lexical structure, as well as phrase structure can be defined using these grammars, and that's the basis for compiling. There's a connection between theory and practice, right? So we know that these two types of grammars connect to the fact that we have two major compiler passes. Parser generators can write code for both of these passes if we use separate grammars, right? So parser generators, gives us the first two-thirds of the compiler by giving us the tools necessary, by producing the code necessary to generate not only the lexer but also the parser part, which generates the parse tree, which can then be used to execute the compiling phase. There's also multiple audiences for grammar, right? So we don't always want to put all the detail into a grammar. Oftentimes, we want a much more high-level version of the grammar that can be used for people to understand what constitutes a legal program. But at the same time, if we're trying to implement an actual language system based on this grammar, we need the exact detailed definition. And that also goes into what the tools need, right? The tools need the exact detailed definition in a machine-readable form so that they can actually generate the parser and the scanner so we can utilize and create the language systems. Anyway, that's it for this. If you look on the sites, the lecture website for this one, you'll see that there's some out-of-class things that you need to go and do. Hopefully you held off and paused the recording when I asked you to start looking up and generate those parse trees and thinking about some of these things. Be prepared. There's most likely going to be a quiz in class at the start of class based on all the things that we covered during this lecture. So anyway, I'll see you in class. Have a great day.